Hi everyone. So today we're going to continue on 9.3. I'm going to try to see if I can finish 9.3 in this video, so that way you can have an extra day to just catch up, because I do plan to have 4 days for 9.3. But if I only need to post 3 videos, then that give you extra day to catch up on what you need to watch. So today is going to be the day we're going to actually talk about what we want to talk about in 9.3, and that will be surface integral. So what's the basic idea of surface integral is that imagine that we have a vector field. Imagine that we have a vector field that is in R3. Let's say given a vector field F that map from R3 to R3. And let's say we're given a surface I'm going to call this surface S in R3, which is parameterized by the function g of uv over some kind of domain D. So important to understand that S is in R3, but D is actually on the UV plane, so technically speaking is in R2. And then we have a vector field that the domain is R3, and they give out a vector in R3. So now what we're going to try to do is try to form an integral of F over the surface S. If we integrate vector field F over the surface S, what we have is called a surface integral. Of vector F over S. So obviously here the important word is the word surface integral. So surface integral is when you integrate a vector field over a surface. We are mainly going to focus on R3 only because of the fact that to deal with a surface in R3, we need to use cross product, and cross product is a operation that only exists in R3. So essentially what we basically try to do is you can think of some way adding up all the vector given off by vector F on this surface S all together. And of course, the major interpretation or application is that this force, this vector field F actually represents some kind of force acting on some kind of surface, and we can try to kind of calculate the amount of the impact of this force on this surface. I actually don't know for a fact what kind of physics property is that, but you ask your physics teacher, he or she might know. All right, so remember, I'm just a mathematician, so I'm dealing with the mathematical part of it. Okay, so how do we actually do that? So, well, let's try to understand what's going on. So imagine the following. Imagine that we have this surface. Okay, and I'm going to purposely draw this surface so that it's not flat. So imagine, all right, imagine that we have this surface right here. So this is my surface S, and it exists in some kind of vector field F, which give a whole bunch of arrows. Okay, so basically meaning like every single point they have some different arrow pointing out, and some of them are long, some of them are short, some of them are pointing this direction, some of them point in different direction. So what we'll try to do is try to kind of collect all these vector that pointing off from this surface together and add them up. Now obviously, how? That's the basic question. So most likely, as I say, this have some kind of physical meaning in physics, and physicists just couldn't figure out how to actually mathematically do this. So a mathematician have to come in and figure it out. So how do we actually do it? Well, how about we try to break it down? So once again, we're going to deploy something that mathematicians use all the time, is to try to approximate what all these vectors add up to first, and then in some way improve our approximation until we can claim that our approximation is infinitely accurate to what we try to do. And therefore, there will be no longer a distinction between our approximation and the actual answers. Therefore, I can say that our approximation is the answers. So that's the basic idea of how that works. So how do we do this? So imagine the following. Let's say we go focus on, let's focus on 1 point. Let's say u sub k, v sub k. Okay? So therefore, I'm not going to redraw the, well actually maybe I do, so that way you can see it. So imagine this is my surface. Okay? Let's try to draw it bigger so you can see better. And let's say here's the point g of u sub k, v sub k. Remember, u sub k, v sub k is in the domain. So the surface S is already formed by the output of this function g. So therefore, this point will be g of u sub k, v sub k. And this should have some kind of vector pointing out based on the vector field f. So therefore, that would be vector f of the position. So that will be f of f of g of u sub k, v sub k. So the problem is the following. To actually calculate the impact of this vector half, what we can do is to, once again, approximate. The problem is that if I move this point g of u sub k, v sub k to a different point, even just slightly, it will change this vector f, because now it's defined using a different position. Okay, so what we're going to try to do is try to assume. We're going to try to make an assumption. What we're going to do is we're going to form a piece of a tangent plane along this point g of u sub k, v sub k. So how do I form a tangent plane? Well, simple. I need two derivatives. What are these two derivatives? dg over dv at u sub k, v sub k. And dg over du at u sub k, v sub k. So that gives me a two tangent vector, therefore allow me to actually form the tangent plane. But I'm not actually interested in forming an entire tangent plane. What I'm interested in is to form a small area where I can assume the vector f is remain the same, so that I can actually have some consistency in calculating the surface integral. So to do that, what I'm going to do is I'm going to say delta dg over dv at u sub k, v sub k multiplied by delta v sub k, and dg over du will be multiplied by delta u sub k, and that would form this two tiny little direction vector. And I'm going to use them to form a parallelogram, which become a small piece of the tangent plane. And I'm going to assume along this parallelogram, the vector f is constant. Okay, so we're going to form a parallelogram of the tangent plane at the point g of u sub k, v sub k. And that parallelogram will be formed by these two tangent vector. So now, why do I want to do that? Well, because now what I'm going to do is I can kind of imagine that this vector pointing out is kind of like forming a prism with this parallelogram as the bottom, and we kind of translate this parallelogram along this vector f, which is the red vector, to form some kind of solid. And if that's the case, I can actually calculate that volume. So to do that, what I'm going to do is this. So once again, let's try to figure out what we are actually looking at here. So we have this parallelogram. Okay, remember, these two sides are formed by dg over du at u sub k v sub k delta u sub k. And this one is dg, maybe right on this side, dg over dv at u sub k v sub k delta v sub k. So we form this nice little parallelogram. Okay, and what happened is we have a vector that points sideways, which is like f at u of, actually I'm going to need more room, vector f at g of u sub k v sub k. And so imagine we basically kind of form this parallelogram again. And we can have some kind of solid. So this volume would kind of represent the impact of this vector field on this surface. So I can now actually approximate this surface integral by just having a whole bunch of these parallelogram prism, and add up the volume to represent what we want as a surface integral. But of course there's a problem. The problem is that this prism is not a right parallelogram prism because of the way the vector f kind of point in a different direction. So I do need to kind of figure out the height of this prism so that I can actually form the area. So how do I form the height? Well, lucky for us, we actually know how to do that. The reason why we do, because we encountered this problem before. We encountered the same exact problem when we're dealing with line integral, where when we have the vector f, which is going in a different direction than the direction of movement. And so now what I need to do is to kind of figure out how to scale the vector f to the direction of movement. And here is the same exact problem, is that in order for me to form this volume, I need the height. So I have to kind of scale this vector f onto a perpendicular height. So to do that, what I need to do is the following. To determine the height of this parallelogram prism, a slanted parallelogram prism, the height would actually be given by vector f dot product the perpendicular vector. But not just any perpendicular vector, unit perpendicular vector. Remember, that's called projection. And lucky for us, we know the perpendicular vector, because that's the first thing we talk about in chapter 9.3. We talk about the perpendicular vector, or the normal vector, is given by the cross product. So therefore, I can now actually form this height by saying this is vector f at g of u sub k v sub k dot product the cross product between dg over du at u sub k v sub k and dg over dv at u sub k v sub k. But because I have to have a unit length, I have to divide by the length of this cross products. And hopefully some of you have a little deja vu, because yes, we've gone through almost exact identical argument in line integral. So now that I have this height, I can now finally try to figure out how to add up all these vectors together. So now I can actually try to figure out at the point u sub k v sub k. I can now calculate this volume right here by doing the following. By saying that I'm taking the height, which is given to be this thing right here, f of g of u sub k v sub k, dot product, the cross product between the two tangent vector, that give us the normal vector. But, ooh, you know what? Actually, I'm going to cross this all out because I'm going to need more room to write. And I now anticipate I don't have room. So let's do it on the bottom. All right, so what happened at the point u sub k, v sub k then? Well, whatever this surface area is going to be, is going to give us this volume right here. So I'm going to now calculate this. I'm going to just call it V for now, but because it's kind of the volume. So V sub k will kind of equal to the height, which is this thing right here. Dot product, our normal vector, which is the cross product between the two tangent vector. But it has to be unit length, so I'm going to have to divide that by that give us the height. So now to find the volume, what I need to do is multiply by the base area. The base area is actually formed by this parallelogram. So how do I calculate this base area of this parallelogram? Well, once again, we also know that because that is something that I already told you. To find the area of the parallelogram is actually given by the length of the cross product of these two sides. So therefore, I'm going to say that is the same thing as this right here. And in case some of you are thinking that, yes, that is our surface area differential. You know what? Give me 1 second. Okay, I'm going to have to move it closer. That we have room. There you go, much better. And then I'm going to say delta u sub k, delta v sub k. Now, some of you might be thinking, why don't you use dg over du, u sub k, v sub k, delta u sub k, cross product dg over du, u sub k, v sub k, delta v sub k for your normal vector? I could, but the problem is that delta u sub k, delta v sub k would actually cancel out when I find the length. So therefore, it really doesn't matter. So that's the reason why I choose not to use it. And as a matter of fact, the perpendicular vector can be found by any length of the tangent vector. So here I just simply choose to use the standard tangent vector to find the normal vector, while to find the area of the parallelogram, I have to use the tangent vector that's modified by how big we want the the parallelogram to be, which is based on delta v sub k and delta u sub k. And notice what's important happen is the following, is that the length actually cancel out. And if you think about it, something just like that happened with our line integral. And so now I can say that this volume would actually just end up being this f of g of u sub k v sub k dot product the normal vector, and no longer required to be normal unit vector because the length that I divided with cancel out. Delta u sub k, delta v sub k. And so that gives me one of these based on this 1 point g of u sub k, v sub k. So now what are we going to do? To find the total impact of this integral over the entire surface S, we are going to try to basically do a whole bunch of these at different points of u sub k, v sub k. So I can then kind of say that this surface integral is kind of approximately equal to the sum where from k equal to 1 to n v sub k, which is just basically the summation k from 1 to n vector f of g of u sub k, v sub k, dot product dg over du at u sub k, v sub k, cross product dg over dv at u sub k, v sub k. Okay, I'm going to try to squeeze in delta u sub k, delta v sub k. All right, hopefully you can see that. I just try to squeeze that in. And so that gives us an approximation of what the surface area is going to be. And this approximation obviously yield a better approximation, a better result if n is bigger. And so now the question is, how big can n go? Well, realistically, maybe like 4 or 5, and that would probably be way more calculation to do. But mathematically, I could potentially let this process go off to infinity. So meaning I can now define the surface integral to actually equal to the limit as n go off to infinity of this whole thing. Summation k from 1 to n vector f of g of u sub k, v sub k, dot product dg over du, u sub k, v sub k, cross product with dv, dg over dv at u sub k, v sub k, delta u sub k, delta v sub k. And yes, if you're thinking, isn't that a Riemann sum? Yes, it is. It is a Riemann sum. And so therefore, I can say that this whole thing now converges because it's infinite sum. So we don't know whether it converges or diverges. But because this is a Riemann sum, we know that it converges to a sum, a value. And that value is what we call the surface integral. So now I'm going to give you the definition of the surface integral. Surface integral. Okay. So the surface integral, let me see, just want to make sure I'm using the correct, okay, yeah, that's it. Okay, so the surface integral would actually equal to, well, surface integral of the vector field F over the surface S defined by g of uv with domain D, and this whole thing is equal to a double integral over D vector f of g of uv dot product dg over du cross dg over dv du dv. So that's our surface integral. Now notice that this surface integral is actually integrating over D, the domain of g of uv, because this is an integral over uv. Surface S will be defined by x, y, z, because that's the output of g. Okay, so that's a little different. Now, here's the interesting part. So this is usually how we calculate surface integral with using the parameterization g. And this results in a double integration. Okay, a double Riemann integral. And that makes sense because the domain of G is UV, which is two-dimensional. So therefore, it requires two integration. That's why this is a double integral. Now, however, just like with line integral, there are two other notation for this surface integral. But before we talk about that, I do want to point out this. Oops. In this expression right here, dg over du cross dg over dv du dv is actually called a vector surface differential. Vector surface differential. So what does it mean by vector surface differential? Basically meaning a small piece of a surface. That's in R3, not on a flat R2 plane. And this vector surface differential is called ds, which we usually just use a regular d for that. So it is something important that you need to know, vector surface differential. And I know I'm almost running out of time, so I'm going to go ahead and do the following. Go ahead and give you two other notation for a surface integral. There are two other notations for surface integral. And if you think about it, it's mirror line integral, because line integral also have three different notation. And if you think about it, the first notation for line integral is the one that involves polymerization, just like what we have right here, a surface integral that involves polymerization of the surface. So the next two are very similar to line integral. The next notation, the second notation for surface integral is this. Is basically the integral over the surface S of vector f dot vector n d sigma. Now, if you think about it, you already know some of these notation. Remember, this right here is a surface area differential. The n is actually the unit normal vector. So therefore, you think about it, this notation basically describes how we form the surface integral. The n is basically this part right here. So if I may, I'm probably going to do this. This is actually called vector n. And this is actually our d sigma. And of course, this is my vector f. So therefore, you think about it, is f dot n d sigma, which is exactly how this notation is written. So this notation you actually will not be using at all, because it's basically no use for you. It's just simply showing you what the surface integral is, but it doesn't help us actually calculate it. So just like with the line integral, we have a similar notation for line integral that I told you you never use it. It just kind of explains to you how the line integral is formed. The third notation, however, is something that you will use. The third, okay, I'm going to draw a line to separate it so that you don't get confused. The third, oops, I'm going to draw right here to separate the second notation. The third notation you actually will use if you have the right information to do it. The third notation for surface integral is actually equal to this. And actually I need room, so I'm going to write on the next line. It's actually called the integral over S vector f dot ds. And I'm sorry, this is actually vector. I'm going to have to write that here. D vector S. That's called surface, vector surface in differential. It's a vector. That's in the word. And this notation can sometimes be written into this, where it actually carry out the dot product for you. So show you what the dot product look like. This would actually equal to vector f. We consider vector f to equal to f1, f2, f3. And so d vector s actually is going to be this. dy dz, dx dz, dx dy. So it's a set of 3 pair of product of differential. And it's actually very easy to remember. Notice that dy dz is in the x position, dx dz is in the y position. Notice y is missing. dy dz is in x position, that's why no x in it. And dx dy, the last one, this is z position, that's why no z. So that's how I remember it. And so this would equal to f1 dy dz plus f2 dx dz plus f3 dx dy. So that is our third notation for surface integral. You will actually use this one provided that you can actually change dz into dx dy, and therefore would allow you to actually rewrite this into a double integral. Because the surface S is actually double. It's a 2-dimensional. So we will do some example together. Unfortunately, my time right now is already 32 minutes. So I'm going to stop right here. And instead of doing another video, if I have time, I might actually spend some class time to do some kind of surface integral with you. However, we're not. Don't worry. Our next section 9.4 is actually talk about using a theorem to calculate line integral, surface integral. So therefore, if you feel like you don't know how to use this notation, is okay, because we'll learn how to deal with it more properly in 9.4. All right, unfortunately, that's all the time I got, so I'll talk to you again in our next video. Okay, bye-bye.